Hi. In this video, we are going to continue with sequences and we are going to talk about periodic sequences. So just like we have periodic functions where the function values repeat after a certain interval, we can define a sequence to be periodic, and this is the definition. For a sequence AN, if there exists definite positive integers t and n naught, such that for all positive integers n greater than equal to n naught, the equality a of n plus t is equal to an is always true. Then an is a periodic sequence with period t starting from the n naught term. Starting from n naught term. Now, what is the meaning of this? So basically, it could be that in a sequence, after you go beyond the n naught term, you have a repetitive pattern, right? So how do we establish the pattern? A of n plus t should be equal to an for all possible values of n as long as n is greater than n naught. So then every time you go t terms, you get a repetitive term. So if that is true, then it is a periodic sequence with period t starting from the n naught term. When we say that n naught is equal to 1, then the sequence is called a purely periodic sequence. Purely periodic because it is periodic from the beginning. N naught is equal to 1, so just after the first term only it starts becoming periodic. Right? If n naught is greater than equal to 2, then it is called a mixed periodic sequence. Because it is non-periodic in the beginning, but after the number of terms exceeds n naught, after that it becomes periodic. So that is the basic definition of a periodic sequence. Let's look at another definition. Let an be a sequence of integers and let m be some chosen positive integer greater than 1 if bn is the remainder of an after dividing by m basically bn is congruent to an mod m, and bn goes from basically 0, 1, 2 till m minus 1, then we call the sequence bn the modular sequence of an with respect to m. So basically in symbols you can write as bn is equal to or congruent to an mod m. Excuse me. So Here we have defined another type of sequence, which is a modular sequence. So you can choose a positive integer m and take the terms of the sequence an and divide each term and get their remainders. The sequence of remainders becomes the modular sequence of an mod m, right? Now we look at some properties of these sequences, so periodic sequences. So first of all, the range of a periodic sequence is a finite set. What do we mean by that? The possible values that the terms of a periodic sequence take will always be a finite number of integers. Why? Because after some point, what will start happening? The terms will start repeating and you will start getting the same values as you got before, right? So you cannot have an infinite set of integers as the range of a periodic sequence because the period has to be a finite integer. So that finite number of terms will have unique values and after that the values will start repeating, right? So that is the logic behind this. Then if T is a period of an, then k times T is also a period of an, also a period of an for any k belonging to natural numbers, for any k belonging to natural numbers. So that is another obvious statement. If the period is some t and then you multiply it with some natural number, then 2t will also be a period of the sequence. Now, another property is a periodic sequence must have a minimal period, must have a minimal period. So there is some smallest possible value of t, which is called the fundamental period of the sequence or minimal period of the sequence. Less than that, you will not see the periodicity show up. So there is a minimum value of that t, that is the period of the sequence. Another property related to these is this one. If t is a minimal period of an and t dash is any period of the sequence an, any period of an, so then t must divide t dash. So basically this is the combination of the previous two properties. We know that if t is the minimal period, then any multiple of t is also a period. So what is true is that t will divide any higher period of the sequence. T divides t dash here, right? And then the next property is any kth order linear homogeneous recursive sequence, linear homogeneous recursive sequence defined by the equation, defined by this equation. We have already seen this in the previous video. An plus k c1 an plus k minus 1 and c2 an plus k minus 2 and so on till ck with constant coefficients, This is the linear homogeneous recursive sequence with constant coefficients. Any such kth order linear recursive sequence is a modular periodic sequence with respect to any integer m, greater than equal to 2. So basically this theorem that we are stating here, we are doing it without proof, but remember what is happening here. This is a kth order linear sequence. We are saying it will always be a modular periodic sequence with respect to any integer m. What is the meaning of that? It means that if you take the sequence of an and take mod m for each term, you will get a new sequence, which is the modular sequence, say Bn for an mod m, and that Bn will always be periodic. That is the theorem. The sequence of remainders is a periodic sequence with respect to any integer m. Okay, now that's about it for this. This is a pretty small section. We'll look at a couple of questions here and then we'll move on to the next topic. Basically, the first question on periodic sequences that I want to discuss is this one. Define a sequence an as follows. An is equal to 1 plus an minus 1 by 1 minus an minus 1. This is true for n is greater than 2 and a1 is not equal to 0 and a1 is also not equal to plus or minus 1. These are the conditions that are imposed. We have to find the period of an of this sequence. If it is periodic, it is not necessary that an is a periodic sequence, but if it is periodic, we have to find the period of an, right? So let's look at the general term here. The general term is an is equal to 1 plus an minus 1 by 1 minus an minus 1. So the form of this sequence should remind you of the trigonometric formula. So if you think about it, tan of pi by 4 plus theta is what? Tan pi by 4 plus tan theta by 1 minus tan pi by 4 tan theta, right? So this becomes 1 plus tan theta by 1 minus tan theta. This is the trigonometric formula and our sequence definition looks very much like that, right? So it might help us if you make a trigonometric substitution. So what we will try is let an is equal to tan of theta n, right? For n is equal to 1, 2, and so on. So then from this relationship, what we are getting is an plus 1 is equal to 1 plus tan of uh, theta n minus 1, right? No, not theta n minus 1. So from the sequence, what we can say is instead of an, we can replace it with an plus 1, that is equal to 1 plus an by 1 minus an. And now we put the substitution. So we get an plus 1 is equal to 1 plus tan theta n by 1 minus tan theta n, which is the same as saying tan of pi by 4 plus theta n, right? So what we are getting is an plus 1 is equal to tan of pi by 4 plus theta n, right? Now, if we use the an plus 1, an plus 1 is we have tan of pi by 4 plus theta n, and we can write an plus 1 itself as tan of theta n plus 1, right? By our definition, by our substitution. So we get tan of theta n plus 1 is equal to tan of pi by 4 plus theta n, right? Now, we can say that this implies that what is our I want to repeatedly use this result. So for that, I know already that an plus 1 is tan of pi by 4 plus theta n. And what is the connection between theta n and that? So we have an is tan theta n. So we can say that tan theta n is equal to I want to connect this to theta of n minus 1. So can we say that tan of pi by 2 plus theta of n minus 1 is equal to this? Because that would mean what? That would mean, okay, right. So from this statement itself, what is obvious is theta n plus 1 is equal to pi by 4 plus theta n, right? So that implies that theta n is equal to pi by 4 plus theta n minus 1, right? And therefore, when I write here tan of pi by 4 plus theta n, I can write it as tan of pi by 4. And instead of theta n, I can write this pi by 4 plus theta n minus 1, right? So that becomes pi by 2 plus theta n minus 1. And similarly, I can write this as pi by 2 plus pi by 4 plus theta n minus 2. So that will become tan of 3 pi by 4 plus theta n minus 2, right? So on, you can keep doing this process, repeating this, writing theta n minus 2 as pi by 4 plus theta n minus 3 and so on. And what you will end up getting at the end of this sequence is tan pi by 4 times n plus theta 1, right? Correct. So what we get at the end is tan theta n plus 1 is equal to this. I hope you understand the sequence of things that happened. We are saying because of this relation, theta n plus 1 can be written like this, and we are replacing each theta n with a smaller theta n minus 1, theta n minus 2, and therefore pi by 4 keeps adding in each step. So if you go from theta n to theta 1, you are adding n times pi by 4. So finally we get the result tan theta n plus 1 is equal to tan pi by 4 times n plus theta 1. And if you want to write tan theta n, that would be tan, instead of n, I will replace it n minus 1. So pi by 4 n minus 1 plus theta 1, right? Now, using this, we can say that we know tan theta is periodic with period pi, So we can use that to predict the periodicity of an, right? How? We can say that this is my an and this is some other term, right? So when will these two be equal? For what values of n? So what we can say is tan theta k should be equal to tan of pi by 4 k minus 1 plus theta 1. And let's say it is same as tan theta k plus t. That should be equal to tan pi by 4 k plus t minus 1 plus theta 1, right? If the sequence is periodic, since an is tan theta n, so if this sequence, if an sequence is periodic, these two must be always equal for any value of k, right? So when will these two be equal? When is this tan equal to this tan? The only way that happens is when the larger angle is n pi plus the smaller angle. That is how you solve a trigonometric equation involving tan. So we should say this angle plus m pi, right? Because when we have tan C is equal to tan D, we can say C is equal to n pi plus D, the general solution, right? So that is what I'm doing. When this is equal to this, I'm saying the bigger angle is equal to this angle plus m pi. Now you can see easily that pi by 4k gets cancelled, and similarly theta 1 gets cancelled, and you are left with pi by 4t minus pi by 4, and minus pi by 4 is also get cancelled, minus pi by 4 plus m pi, right? Minus pi by 4 gets cancelled, and from here pi by 4t is equal to m pi, and pi can get cancelled, and you're getting t should be equal to 4m, right? So m is any in positive integer, so the smallest value when it can start is m is equal to 1, because this angle is actually bigger than this angle. So the first value will come when m is equal to 1, and the period is basically 4. So what we conclude from here is that this tan theta n is periodic with period 4, but already we know that an is equal to tan theta n. So that means our sequence an is periodic with period 4, right? So that is the proof. The next one is this one. Here, a sequence a1, a2, and so on of integers is defined as follows. A1 equal to 1, a2 equal to 2, and for n is greater than equal to 1, a of n plus 2 is equal to 5 times an plus 1 minus 3 times an, if an multiplied by an plus 1 is even, and it is an plus 1 minus an if an into an plus 1 is odd, right? We have to prove that an is not equal to 0 for any positive integer n. So we have to prove that an is non-zero for all possible values of n. Now this is the way in which the sequence has been defined, and we have been given a1 and a2 values. So if you just use the conditions, you can find the first few values of a1, a2, a3, and so on. So we have a1 is 1, a2 is 2. You can see that the product of a1 and a2 is basically 2, which is even. So A3 will follow this definition. A3 comes when you put n is equal to 1, and here A1 into A2 is even, so it will follow this definition. So it will be 5A2 minus 3A1, and that will come out to be 7. And now you can see 2 into 7 is again even. So A4 should be again 5A3 minus 3A2, and that will come out to be basically 29. And A5 would be 7 into 29 is odd. So A5 will be A4 minus A3, and that will come out to be 22. And similarly, you can find some standard values here. A6 23, A7 is 49, and A8 is 26, and A9 is minus 17, and so on. I have found so many values here because I want to make a claim about a pattern that is followed in all the AIs, right? So the claim that I'll make by observation here is that A3k plus 1 is congruent to 1 mod 4. A3k plus 2 is congruent to 2 mod 4. And finally, A3k is congruent to 3 mod 4. This basically covers all possible AKs, because we have divided the AKs into three types of numbers. We have partitioned into numbers divisible by 3, numbers having remainder 1 with 3, and numbers having remainder 2 with 3. So this basically covers all possible AKs, and we are making the claim here that A of 3k is 3 mod 4, A of 3k plus 1 is 1 mod 4, and A of 3k plus 2 is 2 mod 4. We can easily check this now. This is A of 3k plus 1. So notice that it is 1 mod 4. And this is 3k plus 2. This is 2 mod 4. And A of 3k is actually coming out to be 3 mod 4, right? And you can confirm this with all of these numbers. All of these numbers follow this pattern. They are giving the same modulus 1, 2, and 3 with mod 4, right? So basically, I want to prove this claim by induction. So my claim is A of 3k plus 1 is congruent to 1 mod 4. A of 3k plus 2 is congruent to 2 mod 4. And A of 3k is congruent to 3 mod 4. And the proposition's base case is easy to check. Base case is when k is equal to 0. We already know the values of A1, A2 till A9. So we have already checked that. Now what we will do is the induction step. So for that, we'll assume that the statement is true for n is equal to k, is true for k belonging to n. And we want to prove the statement for k plus 1, right? So now here we can check here that A of 3k plus 2 times A of 3k plus 3 will be basically 3k plus 3 will fall in this category, and 3k plus 2 is 2 mod 4. So this is going to be 2 into 3, 6 mod 4, or basically 2 mod 4, right? So it is going to come out to be an even number. Anything which is 2 mod 4 is of the form of 4k plus 2, which is divisible by 2, right? So it is an even number. So therefore, A of 3 times k plus 1 is basically A of 3k plus 4. And since the previous terms 3k plus 2 and 3k plus 3 are coming out to be even, so A of 3k plus 4 according to the problem definition should be 5 times A of 3k plus 3 minus 3 times A of 3k plus 2. And that is congruent to 5 times A of 3k plus 3 is 5 times 3, 15. So that is basically 3 mod 4 minus 3 times 1. So that is basically 2 mod 4. 3 into 2, 6, and 6 is 2 mod 4. So this is coming out to be 3 minus 2 mod 4 or 2 mod 4 or 1 mod 4, right? So for k plus 1, we have shown that it is following the same pattern as A of 3k plus 1. We have assumed that this is true, and when we change k to k plus 1, we are getting it is equal to 1 mod 4 as well, right? Now, similarly, what we will check is A of 3k plus 1 plus 2, right? We have to now check A of 3k plus 1 plus 2. So that is 3k plus 5 actually. But A of 3k plus 4 multiplied by A of 3k plus 3 is what? A of 3k plus 4 is basically A of 3k plus 1. So that is 1 mod 4, 1 mod 4. And A of 3k plus 3 is 3 mod 4. So this product is basically 3 mod 4, which is an odd number, odd, right? So therefore, A of 3k plus 5 should be simply A of 3k plus 4 minus A of 3k plus 3. And therefore, that is 1 minus 3 congruent to 1 minus 3, which is minus 2 or plus 2 mod 4, right? So we have shown that A of 3k plus 1 plus 2, which is A of 3k plus 5, is also following the same pattern of 2 mod 4. And similarly, you can also check for the last case, which is we know A of 3k plus 4 multiplied by A of 3k plus 5 is going to be even Why? Because this is a of 3k plus 1 actually. This is a of 3k plus 2. And we know that those are modulus of 1 and 2 mod 4. So it is congruent to 2 mod 4, which is obviously making it even. So since this is even, we have a of 3k plus 1 plus 3, which is a of 3k plus 6, will be equal to 5 times a 3k plus 5 minus 3 times a 3k plus 4, which will be congruent to 2 minus 3 or 3 mod 4. So basically the proposition that we started with, the claim that we had made, is also true for n is equal to k plus 1. We have established all the cases of the induction. We checked the base case and we have established it for n is equal to k plus 1. Therefore, what this means is an is never equal to 0 mod 4, right? Because always an is becoming 1, 2, or 3 mod 4, right? For any positive integer. So if an is never equal to 0 mod 4, that means that an can never be equal to 0, right? Because 0 falls under what class of number? What residue class? 0 is in the 0 mod 4 residue class, right? But we are never getting an as 0 mod 4. Therefore, an can never be 0. So what we have actually shown here is that the modular sequence of an mod 4, we have done an mod 4. We have shown the modular sequence is actually periodic with period 3. Because we have shown that they repeat in cycles of 3. It is either 1, 2, or 3 mod 4, right? So that helps us prove this statement, basically. So that's all that I wanted to show you about periodic sequences. What we will start off next is a small section on geometrical methods. So we'll be using, I'll be showing you a couple of methods. One is polar coordinates and one is using coordinate geometry in plane geometry. So those will be the topics that we'll make videos about in the next classes. And I'll see you next time then.